Everybody, welcome to lecture 10. Today we'll talk about some more advanced recursive neural network, the kind of network we introduced in the last lecture. Basically, just like the second lecture for recurrent neural networks, today will be sort of a more advanced lecture. So don't be, don't worry too much if you can't follow all the things. Again, in theory, you should be able to. We'll again just take a bunch of matrix derivatives, though we'll have today also a tensor, and I'll introduce the one new equation that you really have to know to understand those tensor derivatives. But in general, you should be able to follow and sit down at home and derive these equations, but you're not really required for the midterm or the problem sets. Unless you want to get some bonus points, I think, for the third problem set, then one of these models today will be important. But basically, we'll focus today on a couple of extensions and design decisions that you can have when you work with recursive neural networks. And these are actually kind of general in terms of general neural network type architecture. So you always have to choose your training objective function. We already know the cross-entropy error. We know the max margin loss, for instance. So we have different kinds of objective or cost functions. And depending on your problem, you might want to choose one or the other. And then we usually have some kind of composition function. In the case of recursive neural network, we're literally talking here about linguistic composition. But in general, you have some kind of different types of functions at your availability for computing a hidden state. Right? The simplest one is just a one-layer neural network or a two-layer neural network. Those are some kinds of composition functions. And this is the main focus of today's lecture, really capturing different kinds of composition functions, understanding sort of how you can creatively play around with these kinds of models. And then we'll also actually, one of the other choices that we won't go in too much today are the different kinds of tree structures that you can use too. So for instance, we already know the chain structure, which is a special type of tree. We know the grammatical structures based on syntactic information that we may have about a sentence. There are actually different types of grammar formalisms too that you could explore. You could also have just the same tree. It's always a balanced tree, for instance. Instead of taking a grammatical structure, you could just have always the same balanced tree. So different kinds of design decisions that you can make, and today we'll mostly focus on different kinds of composition functions. So basically, that will lead us to looking at how we can extract information from standard recursive neural networks, and basically compose kind of a comparison between two sentences, for instance. We'll look at matrix vector recursive neural networks, and this one is the bonus point implementation for problem set 3, which is recursive neural tensor networks, and a very recent model called tree LSTMs. We already know LSTMs from the chain structured models, and it turns out we can use those ideas in tree structures as well. All right, one thing that's important sort of coming up next week, we'll have the in-class midterm. So if you are stuck following problem set 1 and 2, now is really the time to catch up on the material. We'll on Monday basically go over various problem set solutions and look at common problems that people had on Piazza and in the office hours. So the TAs and us and I will have sort of an interactive session that we basically cover again all the material. So if you have specific questions, you're stuck on some derivations, prepare some questions for the next lecture on Monday, and then on Wednesday we'll have the midterm. So, are there any organizational questions around the midterm or the review session? Nope. All right, then let's start with today's lecture. So basically, we'll motivate some of these different tasks and different models based on those tasks. But one thing that you want to keep in mind is that really you could apply any of these models to any of the tasks that we'll cover today. So so far we've only looked at named entity recognition and things like that. Today we'll actually cover a couple of other interesting NLP tasks that are useful to know about. And each of these tasks motivates a different kind of model, but in the end, really, you could use any one of these models for any one of those tasks. Right? They're all they just work better or worse in some cases. And so we'll basically go in an increasing order of expressivity and power, sort of expressive power that these models have. And at the end, I think the current state of the art for at least two of the important data sets are the 3 LSTMs. But there are other kinds of design decisions, and I think this is an evolving field. So expect things to change over the next couple of years. All right, so let's look at the first task, which is paraphrase detection. So what is paraphrase detection? It's basically trying to say whether two sentences have the same meaning or not. And what do we mean by meaning? Well, you could define it as if one sentence is true in a specific world, then the other sentence has to be true as well. So here are two examples. Pollack said the plaintiffs failed to show that Merrill and Blodgett directly caused their losses, and basically the plaintiffs did not show that omissions in Merrill's research caused the claimed losses. So we would say, well, if this sentence is true, then this one has to be true as well in the same world, and vice versa. And here we have a simple example of an obvious non-paraphrase. Initial report was made to Modesto Police December 28th, and it stems from a Modesto police report. They both mention a police report, but they're not necessarily the same. So that leads us to the question of how we should compare the meaning of the two sentences. The simplest thing we could do is just take the last vector that we had computed in a recursive neural network. However, it turns out that if we use the standard plain recursive neural network we introduced in the last lecture, that's really not powerful enough. And so here in this paper that I published in 2011, we actually used all the nodes of the tree, and we computed a comparison based on all the pairwise distances. So what we'll do here, and what you see in this figure, is we enumerate all the nodes of the tree, and we can do that in sort of all the words first, the word vectors from left to right, and then a depth first, right to left kind of tree traversal. And once we computed all the vectors for this sentence and this sentence, for instance, with the model we covered in the last lecture, we can now compute all the pairwise inner products or Euclidean distances. So here we have 5 nodes, and there we have 7 nodes. And so what we can do here is for each of those 5 nodes, essentially compute a distance to all the other 7 nodes in the tree. And so when you have, for instance, cat here and the capitalized version of cats, you would assume that that distance is very, very small. Right? So those two are almost the same. In fact, if you do the preprocessing such that you ignore capitalization, then they would be exactly the same. So basically here, you see this diagonal for things that are very similar. So 2 and 3, eat and catch, might be more similar, both sort of nouns, or sorry, verbs that could be, capturing some kind of animal food process. And then we have basically this original similarity matrix. And now this similarity matrix, of course, depends on how many words you have in each of the two sentences. And we don't necessarily, so one thing we could now do for a neural network is we just take the average value of this similarity matrix. But that would lose the fact that there are certain words in certain positions of the sentence, and that might matter. Right? There's, at that point, you kind of go back a little bit to a bag of words model, when really you want to capture the structure of the two and similar phrases and similar positions of the sentence and so on. And so what we do instead here is introduce a so-called variable size pooling layer that essentially says, whatever similarity matrix I have, at the end, I want to have a 5 by 5 matrix. And so that means I will now define 5 by 5 blocks, so 25 blocks, that basically go over the original similarity matrix and just take the smallest value. And now you might ask, why the smallest value? Well, because the smallest value will indicate that there is indeed something very similar somewhere in that region. So if we take the smallest value, for instance here, we might say, okay, there is indeed, like the main subject in the beginning of the sentence, for instance, is very similar. And then once we have a fixed size matrix, then we can just plug it into a neural network and classify whether this is a paraphrase or not. Are there any questions about this procedure? Yes?
The variable size pooling layer is of a given size to give you a fixed size at the end.
That is exactly right. Yeah. Because the original similarity matrix depends on the size. So you may have to compare, random. You have some sentences with 3 words, other sentences with 20 words. Now in the end, you always want to have a neural network that sits on top of it. And as we all know, our neural networks are usually defined the standard layers such that they have to have a fixed input vector x. And you multiply that with a matrix. Yes?
Does this method care about the structure of the sentence or just the location of each word?
That's a great question. So it does. It cares about the structure. So the question is whether this method cares about the structure of the sentences. It does very much in that it takes all the vectors of the tree. And so if, for instance, the very top vectors here are still the same, then in fact you have very similar tree structures and parse structures. And here in some of these intermediate terms, we will actually compare, sort of on the off-diagonal elements here, we'll compare non-terminal phrase vectors here, so non-terminal nodes in the tree, which are essentially vectors describing entire phrases, and those will be compared to single words. So there's some chance that, going for a hunt and hunting will at some point be compared in this if the parse tree structures work out. Yeah?
I'm curious, so the word recursive that generates the parse tree, is it pre-trained for some other task?
Is that what?
Is it pre-trained for some other task, or do you visualize it randomly?
That's a great question. So yeah, so the question is, are the tree structures fixed or are dependent on this task? And so that is actually a great point, which I should say, which is today we will basically cover different kinds of composition functions, and we'll actually assume for all these models today that the tree structure is fixed and came from the model that we discussed in the last lecture. So we just assume for any given sentence, we're given the sentence with the words as well as the tree structure. And now we're just learning, we basically assume syntactic information is fixed and set. Now we're trying to understand the semantics better of the sentence. That way the model can really focus on the semantic tasks that we care about, assuming the syntax is fixed. Great question. All right, so in 2011, that kind of model created state-of-the-art performance on the Microsoft Research Paraphrase corpus. And while that was great, this is one of these examples where you do research and you're close to your data. And at the end of this project, we looked at the errors. And at some point, we looked at several of the errors and we're like, actually, I sort of agree with the model more than with the ground truth. And this is something that you'll also observe when you do real life and you work with real data, that sometimes your annotators might not be very accurate. And so we sort of moved away from this task, and at the end of this lecture, we'll actually look at a much better evaluation that will be continuous. Because in many cases, there are fine gradations of whether two things are similar or not. They might not be a perfect paraphrase, but saying it's either a perfect paraphrase and has exactly the same meaning, or it is 0 and is absolutely not the same, is not as helpful as having some fine gradations and say like some random number between 0 and 5 might capture the similarity. And if it's 5, they're exactly the same. But if it's 4.3, they're still quite related. So we'll actually look at a better data set. One thing that is interesting still that came out of this work is trying to visualize what's happening in neural networks. And that is something that I also encourage you all to do in your final projects, is really try to be close to your data and also close to your neural networks that you implement. You really want to try to visualize as much as you can and gain intuition of what's going on. So here you see an actual set of similarity matrices that come out of that model. So you have here the ground truth labeled, so the first 3 are paraphrases and the last 3 are not. And you have the probability that this model assigns, again just trained with softmax classifier at the end, the probability that this model assigns to those 2 sentences being paraphrases or not. And here you see an intermediate visualization of exactly the top of the similarity matrix after you basically pooled things together and found the the minimum value in these different regions of the original one. And so you see here that for things that are very obvious paraphrases, you do indeed get a very nice diagonal structure, where in the first block here, we're actually just comparing words to other words. And you see here that, well, a lot of the words here are perfectly aligned. And in the 2 blocks here on the off diagonal, you actually compare phrase vectors to word vectors of the other sentence. And then at the bottom here, you'll compare phrase vectors to one another. And the interesting thing here is, even in the phrase vector part of the similarity matrix, you see a lot of very small values, meaning there are some phrases that are very, very similar to one another. And that was a very interesting insight. And so basically, this is a very obvious paraphrase. Here's an interesting one. One, it's ungrammatical, and 2, you have sort of 2 blocks that are really shifted. So the lies and deceptions from Saddam have been well documented over 12 years, and it has been well documented over 12 years, some ungrammatical instruction here, of lies and deceptions from Saddam. This is a data set coming from news, and there's an actual grammatical mistake. But the model here basically realizes that there are 2 phrases that are very similar, but they're shifted. And that really results in a similarity matrix that has these 2 off-diagonal lines here. And even in some cases where it's less obvious of a paraphrase, there's no nice diagonal structure, the model can still recover that these are similar. And likewise, despite having sometimes nice structure that looks really good, there's still, this here barely got it right for not being a paraphrase. This one here is actually kind of interesting. Who here has an idea of how we get to this gap structure here? So we have these 2 diagonals, but we have a gap in the middle. Where does this gap come from? Yeah.
What?
Yes. Sorry, what do you mean?
Some type of negation.
No. Yeah.
The first one basically has an entire closet that is missing.
Exactly. It has this entire clause here that Henry Kissinger was an ambassador at large for counterterrorism, and that whole fact here is missing from the other sentence, and that breaks the mutual sort of entailment relationship that if one is true, the other one has to be true as well. And so here you basically see that this is captured in the similarity matrix. There's some information missing in the other sentence. And this again could be helpful if you wanted to work on summarization, for instance, and want to use the sentence that includes the other sentence but has more information. And here's an obvious one where if you see a similarity matrix like that, they're obviously very different and not paraphrases. All right, so this is one way for you to understand how to take out features from a neural network and play around with them in other ways. And what's nice about this kind of model here is you can actually take derivatives of the entire thing from start to finish. So you have here, is this a paraphrase or not? You do your standard error messages down through delta. Then here you have the smallest value. And this is an interesting way and something interesting to think about for you at home. What happens when you take the derivative? Well, the value here is the smallest value coming from here. So all you need to care about is the backpropagation through the pair that is the smallest. And then those will send deltas to exactly, these 2 here will just be inner products, just like your word vectors were inner products. And you can take derivatives and propagate those all the way into the tree. So this is a nice way to design your model. You always ideally design your model that if you have enough data, you can look at the very top and propagate your errors all the way down to the very lowest level, which is usually the word vectors. You might not always want to do that if you don't have enough data and you have too many parameters, you might just overfit. But it's always nice that if you had enough data, you could actually backpropagate through the whole model. Yeah?
Isn't this paraphrase model kind of, it's really sort of based on word similarity?
Yeah, so definitely the word similarity here plays a huge part. And you can get, well, you can actually see one other problem with this data set here is that basically almost every model gets some reasonable performance at some point. And then it's really about pushing the performance higher and higher. Yeah.
Okay.
So yeah, the phrases only give you a slight boost over what the word vectors already give you.
I was just going to ask you what the gap is there.
Yeah, it's a couple % but those couple of % here matter a lot because, I mean, yeah, this data set is problematic. Like I said, there are actually some models here that people had published, and I don't mention some of the really bad ones. But if you just said everything is a paraphrase, you could actually do better than some published papers on this data set. So, which I guess is another interesting. So this comes from the data set being imbalanced, and so if you have, for instance, 65, say, or 70% of all the labeled examples in this data set are a paraphrase, then you could just do a simple majority vote classifier and says, well, everything is a paraphrase in the data set, and you may get to some number as like 65 or so. And then some people publish papers, and their method, after doing lots of fancy math and complex optimization, got to 63. And so basically, had they just run a proper comparison and looked at F1 metrics instead of accuracy and built like some simple baselines, they would have noticed that and not embarrassed themselves in front of the academic community. And this is something I encourage you also to do in your projects, which is try to run simple baselines and make sure that whatever model you have in the end actually works better than your very simple baselines. Yeah.
Is the reason why it's like an autoencoder rather than just the vanilla kind of bottom-up recursive neural network has something to do with the fact that there's fairly sparse data and you need to have some like meaningful representations, and so you use an autoencoder as a pre-training?
Right, so I skipped a little bit here, which is there are different kinds of objective functions that I mentioned, and we actually used a different objective function here, and since I didn't introduce that, we'll probably take the question offline. Yeah, it turns out there are also ways to train these recursive neural networks in an unsupervised way, where you just try to encode the input itself, and it's kind of a dimensionality reduction kind of idea, but it's beyond the lecture, so we'll talk about it afterwards. All right, so that was a standard recursive neural network, and the task was paraphrase detection. So let's look at some more powerful way to compute our parent vector. So far, all the time we computed the parent vector, we used the same simple equation here where we concatenated the two children and then multiplied it by W. And of course, and then applied an element-wise nonlinearity, and we had our bias term. But basically, this is just one affine, simple linear matrix multiplication followed by nonlinearity. And that really is clearly not that powerful a way to compute a parent vector. And so one way to make the composition function more powerful was to untie the weights W. So we had a different W for adjective and noun compositions, and a different one for verbs and noun phrases and so on. But what if one of the words acts mostly as an operator on the meaning of the other word? So for instance, we could see very as a operator that operates and amplifies whatever adjective comes afterwards. So if we say very good, we may think of good as a vector in a certain direction, and if you say very good, you elongate that vector. And so this led us in 2012 to think of a new kind of composition function, namely a recursive matrix vector neural network, or a matrix vector recursive neural network, where essentially we will represent every word as not just a vector, but also a matrix. So instead of saying every word is now only this n-dimensional vector, instead we will say it is an n-dimensional vector and an n by n dimensional matrix. So huge blow up in number of parameters here. And there's some nice linear algebra tricks, namely low-rank approximations to matrices, which we won't go into to reduce that again. But basically, that is the idea. And so let's look at how we now compute the parent vector. Basically, what we'll do is we'll take the matrix of one word and multiply it with the vector of the other word. And we do that same thing for the other one. So you have here very good. You take the matrix of very, you multiply it with the vector of good. So essentially, you now have an input-specific neural network. Right? This one here you can see as basically just a linear layer, but that linear layer now depends on the other word that we're composing. And then we apply the standard W matrix, add our bias term, and have a standard nonlinearity here. So it's really, this is still somewhat of a standard neural network. It just happens to be that your composition function depends on the inputs themselves. Are there any questions about this model? One interesting question is, well, what do you do after the next step, right? And so basically, for each parent now, you'll have to compute also another matrix that now represents that whole phrase. And that, again, will just be a simple neural network. And then we can basically repeat this kind of operation at every node in the tree. So this is a much more powerful model, right? This model can now change the parent vector depending on the children. In fact, you can think of this here as a way, as another step in the direction of that we took when we allowed different W matrices depending on the syntactic categories. Now you kind of have different W matrices because you could essentially these two here will be multiplied. So you can again write out W here as these two blocks. Left block multiplied by the left child, right block multiplied by the right child, and that will then modify, basically W1 times C2 here. And so what that means is instead of having different matrices for different syntactic categories, we have different composition matrices depending on what the actual words are. So what is this kind of model by us? Here we looked at an interesting sentiment distribution task where we have, for certain words, we can look at the statistics of how often a certain bigram or pair of words appears in movie reviews of a certain star rating. So you can go through all of IMDb and you look at how often does fairly annoying appear in 1-star movie reviews, 2-star movie reviews, and so on. And you normalize this to be a standard multinomial kind of distribution so that these numbers sum to 1. And then we can look at how powerful, how much can a standard recursive neural network modify and predict these, and how accurately can it do that, versus an MVRNN, which is this matrix vector recursive neural network. And we can basically see that for a lot of things like attenuators, so fairly is a so-called attenuator, it makes things less strong. So if you say annoying or awesome or sad, and then if you say fairly, any one of these adjectives, then it's somewhat less pronounced. And in that case, both of the models kind of can predict that reasonably well. Where the model, the MVRNN really shines here is in negation. In that negation, you really want to change the sentiment substantially. And so annoying, if it's not annoying, it is much flatter for the MVRNN, and especially awesome here. Basically, the RNN, when you combine not awesome, you have the same matrix W for all the different ways you could combine bigrams. The standard RNN is still very positive and still predicts that not awesome appears much more often in high star, very popular movies, but the MVRNN was able to really attenuate this because it changes the composition and realize, okay, if it's not, then it really modified the sentiment. And this one here is actually one of the more interesting ones. It's this kind of U-shaped curve here. So here we basically, both models correctly predict that unbelievably sad appears in very negative reviews as well as in very positive reviews. Does anybody have an idea of why that is? Some linguistic intuition? Yeah?
Well, in the positive reviews, the movie is effective at inducing pathos or whatever. And then in negative reviews, it's just really terrible and you're sad that you went to the movie. Exactly. So here it's sort of a pathetic performance of the actors, for instance, and here it's like Titanic or something is really emotional. People love sort of tearjerker movies.
So this is kind of interesting that the models figured this out, but of course this is because we only had a bigram. And we looked over the entire statistics over these large documents. Now if we used, for the next couple of layers, we combined the sentences, then hopefully we could disambiguate and change the distribution that we predict for the overall sentence. Yeah?
It seems like there's actually not a whole lot of change you have to put in the two different models.
Mm-hmm.
Incorporating this extreme, given this specifically for these modified words.
So it can be for all kinds of other words, but you're right. You see here, it basically gives you only slightly improved performance for some of these tasks. And this is what we often observe. A lot of times, a simple model will get you, sort of 70% of the way there. And then it's about, well, do you really want to have a model now that, quote, understands that when you negate something, it really changes the meaning. And so this is really just one way of doing that. And to be honest, the reason why I'm mentioning this first and not last is that I think the models that come after this will actually be more powerful and are probably the better models to implement. But I don't want to just sort of give you here's the final answer of what we currently think is the best model, because honestly I think this is such an active area of research. This will change over the next couple of years. Instead, I would like to show you sort of the progression that the field has made over multiple different kinds of models, so you can try to better extrapolate and maybe be part of that community to find the next best model after this. So I don't think MVRNNs are the final answer, and I think the model that comes after this and the final model are even better. Yeah?
What are the graph tools for the other graphs there?
So here we basically show a couple where there is no ground truth, and because we took those out they're not part of the test set. But here, so not SAT, for instance, this in red here is actually the ground truth that you would have wanted to predict, but you also see that it's a little noisy. So one interesting thing, and this again is a typical example of we could really use any recursive neural network for this kind of problem, but it turns out at the time here the MVRNN worked the best. And this model here, or this task, is basically to try to classify the relationship between two words. So for instance, is this a message and topic? Is, the movie showed wars. The movie here is a type of message, and it had as its topic the term or wars. And you have other kinds of things you could try to extract, such as cause and effect. So imagine you want to work in the medical domain, and you want to have your algorithm read a bunch of literature and say, this medication affected a patient in this way. So cause and effect. You now want to read a bunch of medical literature and extract all these facts so that you can eventually build a large knowledge graph and then help answer questions that people have later. And so, you might say avian influenza is an infectious disease caused by type A strains of the influenza virus. And now, influenza and virus are in a specific relationship, namely cause and effect. And so there are basically 20 different kinds of relationships, and we want to classify them in between, and this was actually a competition. And so what you often observe in competitions, both in sort of Kaggle, but also in natural language processing competitions, is people add more and more features to their models in the hopes of they look at an error and they say, oh, I could fix that error if I add this kind of feature to the model. And so as it goes in competitions, people really try to get the very best performance. And so in order to solve this kind of task, people used a linear classifier, an SVM. But then they put in part of speech tags, these taxonomies in WordNet. They looked at a bunch of prefixes and other morphological features on the words. Oh, PS here again, sorry. Dependency parse features. So this is basically a specific type of grammatical analysis. And then a bunch of word classes. PropBank and FrameNet are actually very large resources that try to enumerate all the ways you could have certain semantic frames. So a frame could be, for instance, going to a restaurant. And then going to a restaurant might include paying your bills, ordering your food, and things like that. and so on. Basically, a gigantic tool, and Text Runner by itself is actually a model that tries to go over the entire internet and find various specific relationships, some of which are actually exactly the same here. So we have instrument agency, for instance, or cause and effect are part of the feature. So it's a completely different model trained on gigantic corpus and so on. And so when you take your nice, clean neural network model and you only train it on this data set, then these various models couldn't do quite as well. They basically were still 3% short. And so in the end, what we did here in order to publish this paper, and this is something that you can also do if you're desperate and you want to, you basically realize that your data set itself doesn't have enough information. It's just not big enough. There are certain examples in your dev test, and you will notice the only way you could ever get this right is either by adding a specific feature to get this example right, or by having more training data. And in this competition, you just have a fixed amount of training data, and so the models cannot learn certain things. And so we ended up also adding part-of-speech tags, WordNet features, and named entity tags, and that way the model could then outperform this other model here with tons of different features. And this is sort of suboptimal. I think a nicer way, if this wasn't a competition, would be to actually just collect more representative data. And that way, that's usually very fast. You just continue letting your annotators run on other kinds of data, and then you don't have to add manual features. All right, so we brought up sentiment detection before, and I mentioned, so this is the next task, and the next model, which I actually think is a really interesting model, and this will be one of the bonus points for problem set 3. Basically, sentiment detection. It's a very fun task that is close to both the academic community, because it has these interesting subtle notions, as well as immediately useful in industry. A lot of people are using that for trading. I had brought up this example here of Anne Hathaway before, who starred in a good movie. Movie reviews came out. Stocks from Berkshire Hathaway, the company, went up. And now, hopefully, if you were to work ever at some kind of hedge fund or automatic trading company, you would know to not make that mistake by running proper named entity recognition and then sentiment analysis. And so what do most people do? And this is kind of an interesting sort of historical perspective here on why these models are interesting. Basically, most people, when they did sentiment analysis in industry, would just use a bag of words representation, and they add more and more linguistic features and processing to it. So they might define these regular expressions for negation. They may have sentiment lexicon and say, all right, this word is always positive. And that inevitably runs into trouble. So you might say, you're thinking about movies and books, and you say surprising. Surprising is a positive word. And you just say, all right, I have now my dictionary, my lexicon of all the positive words and all the negative words, and I say surprising is a positive word. And then you try to run it on a car reviews, and the steering was surprising, and that's very negative in that context, right? And so you don't want to necessarily predefine these and say this is always a positive word. You want, ideally, the models to learn this from data. The other thing, of course, is that when you use bag of words representations, you can't really distinguish between some very important differences. So here you have white blood cells destroying an infection and an infection destroying white blood cells. If you were to work in the medical domain and you read one in your report, you might live, and the other one you might die. So it's very important, but a bag of words representation couldn't distinguish those two things from one another. That is, however, again, one of these examples where you can get a lot of the way there, right? If you have very long documents, you can get into the 80s, or for some simple cases, even into the low 90s in terms of accuracy, and that is often because there are a lot of very easy cases, right? If you see the word horrible in a movie review, it almost doesn't matter if you have some negation somewhere. If it's not horrible, it's still not going to be a positive movie, right? So you can get some way there, but it's still kind of unsatisfying because it's obvious that the model could be very easily fooled by just adding some words here and there. And especially when it comes to single sentence movie reviews or just shorter phrases that we now encounter more and more on Twitter, for example, then the accuracy is has never gone for the specific data set by Pang and Lee from Cornell over 80% in the last 7 years. And so what we found when we analyzed this data is that basically once you want to push above 80, then you actually have to start understanding negation and the scope of negation, for instance. And I'll explain what this is right here. So here we have two sentences that were incorrectly classified by all these simple bag of words classifiers. You have the movie Stealing Harvard, this silly comedy movie. So Stealing Harvard doesn't care about cleverness, wit, or any other kind of intelligent humor. Right? And what these bag of words models do is they just have a weight for each of the words, and then they sum up the weights. And for, you would assume negative words have a negative weight and positive words have a positive weight. You sum them all up, and you say, all right, this is the overall sentiment. And now here you have humor, intelligent, kind, wit, cleverness, care, lots of positive words. Yet you have this one doesn't in front of it. And you have to understand that now doesn't actually has a scope over the entire rest of the sentence and really negates all these things. And so another interesting example here is a so-called contrastive conjunction. What is a contrastive conjunction? It's basically a conjunction that combines two subphrases, but it contrasts them. And but is the sort of standard prototypical example of that in English. And you have the sentence here, there's slow and repetitive parts, but it has just enough spice to keep it interesting. So now we see that while there's something negative here, you then contrast that with something positive. And when you use these kinds of constructions in English, you usually assume that what comes afterwards is actually positive, is what actually matters in the sentence. So in this case, after the but comes something positive, so we say this is overall a positive sentence. And so we basically found that there are two things missing to really push the performance on this kind of data set. And the first one was to have actually compositional training data, in the sense that we want to actually have a model in order to analyze and train the model to really label every single phrase in a sentence. And in the end, we also had to have a better compositional model. And so what we did is basically we went on Amazon Mechanical Turk, and we collected for all the parse trees of the original Pang and Lee data set, all the phrase labels with this kind of interface. We basically just showed people for a specific subphrase, you have a little slider, and you'd say, how positive or negative do you want this to be? And this is also a good example of, if for a project. If you actually wanted to solve a new task that nobody had yet solved, and there is no data set out there, then Amazon Mechanical Turk is probably the best way to go and collect that kind of data. If it's English language and it's something that most normal humans can do, you can use Amazon Mechanical Turk and collect your own labeled data sets. You probably won't be able to get 200,000 very accurate labels because that will cost you a couple $1,000s. But you can get maybe 10,000 or so. And in this case here, because Amazon Mechanical Turk and most other crowdsourcing platforms aren't perfect, these are basically people that get like 1 cent for making, for reading 5 sentences and assigning a positive or negative label to each sentence or phrase. And so sometimes they just say, whatever, I just want to get the money, and they just click negative, 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 and move on to the next task. And so what you want to do is basically, and these are all kind of interesting sort of facts for real life machine learning kinds of projects, you're going to want to actually have 3 different people label the same phrase, and then you can do a majority vote, or you can ignore certain labels that were very inaccurate or very different to the other 2. So now with this kind of data, we can really actually train these models and evaluate how well they do once you really combine them at the interesting parts of the tree. And here we have a very nice visualization by one of the co-authors of this paper, Jason Chuang, who basically visualized for different n-gram lengths what is the distribution over labels. So we notice here that for single words, so the n-gram length of 1, most normal single words are actually neutral, and you have few of these sort of awesome, fantastic, wonderful, very positive sentence phrases or single words, and few very negative ones. And then on this particular data set, as you get to longer and longer n-grams, you basically have more sort of composition that generates the sentiment. And this is also, this is like sort of one of the most beautiful visualizations of a data set that I've seen in a long time. So that's kind of a high bar. But again, for your projects, I want to encourage you to really visualize your data, especially if it's a new kind of interesting data set. If you just use the standard sort of data sets other people have used, like this one, which is available in a potential class project, then of course it's less interesting. But if you have your own data set, try to visualize what you're trying to predict and what your data set actually contains. And what we also noticed here is that basically if we can, originally we had this slider, and the slider had various, like I think it had 25 sort of in-between positions. But really we captured, we could see that we capture most of the variance of this data by just making it a 5-class classification problem. We have here a very negative, negative, neutral, positive, and very positive class. And this, in some sense informed our evaluation metric that now hundreds of other researchers who use this data set now also use. So it's pretty important as a pre-processing step to understand your data. So we look here first at the original evaluation metric, which was just positive, negative on the entire sentence. And basically just look at the entire sentence classification. So not looking at the subphrases, just looking at the root of all the nodes. And we notice that basically all the models, including simple baselines, actually get better. So this is something very typical also. Whenever you have a certain model and you have a certain amount of training data and you don't feel very creative, you don't want to implement a fancy new model, this thing you can always do to just improve your accuracy is collect more data. Of course, that's not going to be a very interesting class project, so don't do that for this class. But in general, if you're in industry and you just really need to improve your performance in your job, then for the model that you have to implement, just collect more data. However, when we analyze now the resulting models, we found that the hard negation cases, such as the stealing Harvard example, were still almost all incorrect. And so we figured we need a more powerful model, like 2 or 3% wasn't enough. And so this led us to the following interesting recursive neural tensor network, which is much more expressive than the previous RNNs, including the MVRNN. In fact, it outperforms the MVRNN. And the main idea here is that as you generally go deeper in your models, you get more interaction between your inputs. But if you go deep inside each node of a tree, then you will very quickly create a very, very deep network, right? It will be crazy deep in the sense that if you have 3 layers at every node, and now you have 5 nodes of your tree, now you have 5 times 3 layers. So you have many vanishing gradient problems, exploding gradient problems, and so on. And we wanted to basically create a composition that allows for immediate multiplicative interactions between the numbers that you have in your 2 child vectors or your 2 word vectors in the very lowest level. So again, just to remind you, we have here a fixed tree structure. We have word vectors that you've all implemented in pset 1. So we have word vector here for not, one for very, one for good. And now we want to basically compute in a bottom-up fashion the phrases and phrase vector representations, and then we basically classify those as well. And again here, not and very and good, you can also classify the word vectors directly. All right, so how do we do this? Let's walk through this model one step at a time. And please raise your hand if you have a question about any of the steps. So the first thing we do is we concatenate the 2 vectors, in this case B and C here, as before. But now we have this sort of bilinear form where we actually have here, let's assume for these visualizations that all our vectors are just 2-dimensional. Again, of course, they will be more like 25 or higher dimensional than that. But for illustration, they are 2-dimensional. So we'll create here a concatenation of the 2 child vectors. So we'll have here a 4x1 vector. And then we take that same vector and we just transpose it. So we have here a 1x4 vector. And now the way we can get an interaction is with this bilinear form where we have this matrix, which is now a 4x4 matrix, and we just multiply this. So what will be the dimensionality of the result? 1 by 1, exactly. So 1 by 4 times 4 by 4 times 4 by 1 results in a 1 by 1 number, but of course we want to have in general n dimensions, and in our case 2, because the resulting vector should have the same dimensionality as the children, so that we can now reuse it again recursively in the next higher layer of the tree. And so basically what that means is we'll just have multiple such slices, and each slice has a different set of weights. Okay, so in general, if we have 25 dimensional word vectors, we'll have 25 of these 50 by 50 matrices. And we'll write this here. In our case of the just 2 dimensions, we have basically 2 such slices in the tensor. So tensor just being a 3-dimensional matrix, right? And each slice will compute an intermediate representation for that node in the tree. So, for that node in the vector. All right, so then we add our standard neural network, which is just this linear transformation. You can kind of see this here also as a quadratic interaction, right? Now B and C will actually interact directly, and B also will interact with itself here in a quadratic way. And then we'll apply our element-wise nonlinearity to the sum here. And this is a model that I introduced 2 years ago in a paper here, Recursive Deep Models for Semantic Compositionality over a sentiment tree bank. Sentiment tree bank being the data set I just showed you. Yes?
You alluded to this earlier, but is it sensible to use a low-rank decomposition?
Yep. That's a great question. It goes a little too far for this class, but in general, whenever you have a matrix W, you can have decomposition into a low rank, where you say, if your W, for instance, is an n by n matrix, you can represent U here as an n by rank, where rank, if n, for instance, is 100, then maybe your rank can just be 10. And now you represent W here as an n by R, which is your U matrix, and another one is an R by n matrix, so that the resulting matrix will again be an n by n, but you actually have a low rank approximation. Here you have many fewer parameters that you have to learn. Side note, don't worry if you're not familiar, but in theory, if you took linear algebra, low ranks should be something that you're familiar with. Okay, so how do we take derivatives of this tensor beast here? Well, there's really only one new piece of math that you have to learn, which is what is the derivative of x when you have this kind of form A transpose x times A. And again, you can write these out in all the gory details. Just take out all the indices, write it out, and you'll come to the simple fact that it's just A times A transpose, so you have this outer product here. There's also, at some point, you kind of internalize these matrix derivatives so well. There's a neat document on the internet called the Matrix Cookbook, and it's a fun sort of, well, depending on your definition of fun, but it's kind of an interesting way to just see all the various matrix derivatives that you can have. And it's actually kind of interesting. And this is one of the typical examples from the Matrix Cookbook. So once you feel like, I could write all the indices, but I have enough intuition because I've done it many times, you can just look at the Matrix Cookbook and define your own, or look very quickly at what the derivatives are. So let's write out a couple of the intermediate steps in case you really want to tackle this as your bonus point project for problem set 3. So basically here we have our standard softmax now on every single node of the tree. So we have here the superscript A for a specific node, and we have our prediction Y. And we use the same cross-entropy loss that you've derived before. We have the same standard softmax error message that you've derived also at the top of the first node. And now the main difference is that we have these outer products as updates for each of the slices of the tensor. And the delta message here is a similar kind of delta message. We just have it for the kth element of that delta. Basically modifies the kth slice of the tensor. And that results in this final main backprop rule, and you should all be very familiar with this rule now. If you took out S here, you basically have your standard W transpose times delta times, this is again the Hadamard product. Some people use different notations. Sometimes you have a little circle, a big circle, cross circle, whatnot, times F prime of this. So without the S here, this is an equation that you should all really familiarize yourself with, especially for the midterm. And it's actually something that once you understand that equation, without the S term here, don't worry about the tensors, but once you understand that equation, really all of deep learning and these neural networks not really lose their magic. They're still kind of amazing, but you kind of really feel like you got it. You understood how to do this, and then you know, research and applications of neural networks will be very obvious to you. The S term here is a little more tricky. Basically, you know, it'll boil down to this this formulation here. So don't worry if you know that isn't as intuitive as the first part should be. But again, I think you have the tools now to really write it out and try to arrive this yourself. And then this, as before, we actually split our derivatives into two parts, one for the left child, one for the right child. All right, so basically we can use this model now, and we get another nice boost here and actually push this to 85. And what's more interesting is, because of this interesting new data set, we can now actually analyze, you know, where does this model work better, and not just look at the root accuracy of the full sentence, but actually look at all the subphrases that we have in each sentence. And when you basically compare now, these various recursive models are much more accurate than simple sort of averaging of the vectors. And the RNTN is basically upper bounding in almost all different n-gram lengths in terms of accuracy, all these other models. What's most interesting to me were these negation results here. So we basically created a very hard subset of this data where we took sentences that were either positive or negative, and we tried to almost have an adversarial setting here where we tried to build examples that change the original sentence as little as possible, but change the sentiment entirely. So maybe just changing one word in one sentence, but now really modify the sentence entirely. So basically, this measures how easy is this model fooled by a human who wants to write a tricky sentence. So here we have Roger Dodger is one of the most compelling variations on this theme. Versus Roger Dodger is one of the least compelling variations on this theme. And we really see here that the model captures that once you say it's least compelling, that is actually negating the compelling, and that goes all the way up to the tree and becomes negative. And most compelling is very positive. So then we said, OK, let's actually not look at a bunch of examples, but really look at an accuracy on this negation set. And basically, we found that most of the methods were essentially able to capture that negation makes things more negative. That is actually an interesting linguistic result from Chris Potts, a linguistics professor here, from 2010, where he shows that when you talk a lot with negated kinds of sentences, then you are actually often expressing negative sentiment in terms of how people receive it. And so we see here, in terms of the accuracy on the subset, that really the RNTN now is 20% more accurate than the MVRNN, and over 50% more accurate than a very simple baseline. So once it comes to really hard examples, this kind of model really starts to shine, and you feel like it has a much better sense of what's actually going on in a sentence. But in general, we can look here at exactly the nodes where you have something positive phrase, and now you add a negation, and now it becomes more negative in terms of the probabilities that you take away. So this is the change in probability mass on the positive and very positive and neutral classes. So then we were slightly worried, what if all this fancy RNTN model did was just basically see negation and make it more negative, right? That wouldn't have been that interesting. Fortunately, we then went ahead and created another data set, a subset of this data, where we had negative sentences, and then we negated those. And what you ideally would see there is that the neutral probability increases, and the positive probability increases. So here we have an example, not. Not as a negation by itself is often slightly negative. Bad by itself is predicted to be very negative. But once we look and visualize the resulting probability, this is basically the output here of our softmax classifier, we actually realize the model is indeed able to not just sort of average or take any negation and make things even more negative. It actually was able to predict a neutral class with a little bit of positivity. And this was quite exciting for us. So then we looked at a couple of more examples. It's just incredibly dull versus it's definitely not dull, becomes neutral. When you say not dull, that doesn't mean it's necessarily super exciting, but it's less negative and more of a neutral thing to say. And in terms of the accuracy, we see a huge improvement again. But what was most exciting at the end of this project is that we found that the RNTN was actually the only model that not just quantitatively but qualitatively was able to capture this effect. That when you have a negation and something negative, the probability mass of the neutral and positive classes should increase. And this is like, this is sort of a very nice way to, like, if you have these kinds of analyses in your own class projects, then I really know you were close to your data, you really understood what was going on, you understood why this model worked better than the other model, and you didn't just have, one final table that said, well, accuracy improved by 1 or 2%. You can actually really, see why it improved and on what examples it improved. And this is another sort of fun way you can look at the entire def set and basically extract all the phrases that fire most strongly for a certain class. And because we don't just use unigrams and bigrams, we can actually look at even the most positive or most negative 5-gram or trigram or even 8-gram for these movie reviews. So a trashy, exploitative, and thoroughly unpleasant experience is one of the most negative 8 grams that the model could fish out from all the movie reviews. And there's some really fun ones in here. And once you propagate all the information to word vectors, you'll also see some interesting patterns. But let's move on to the last model, which is also very exciting, and I actually think it's probably the currently best model out there. Basically, I hope you still remember the LSTMs, the long short-term memories we talked about, I think, last week. Historically, those were only over temporal sequences. So what I mean by this, again, we have just these chain structures, and every node of this chain, we basically have one word vector x coming in, and we have one output prediction y from a softmax. And this were the equations of the LSTM. We had our input gates, our forget gates. Those were just standard recursive, standard neural networks with a sigma nonlinearity that was between 0 and 1. We had our output gate, and then this is the new equations that were used in this paper. I'll mention in the next slide. But basically, instead of the C tilde that we used last week, they just use U. But everything else is the same. Here again, instead of having the Hadamard element-wise multiplication, instead of having a little circle, they use a circle with a dot. Again, this is, I hope, when I introduce you to these different kinds of notations, you eventually can read papers, look at the equations, and you see the semantics of the actual equations despite having slightly different notation. So the dot here is basically, again, just an element-wise product. And then we had our output. The final output was basically a 10H layer of our memory cell here times the output gate. OK, so that model is pretty advanced already in a chain structure. And it turns out we can use that exact idea also inside a grammatical tree structure. And this paper isn't really quite out yet. It's just accepted to ACL, one of the major NLP conferences, which will happen in the summer. And there's basically a great student, Kai Sheng Tai, who's in Chris Manning's group. Me and Chris Manning are the authors of that paper, which is titled Improved Semantic Representations from Tree-Structured Long Short-Term Memory Networks. And that is already a mouthful, and the equations also are not getting any easier. But I think you'll notice here, again, these are just the Lego pieces that we very carefully defined and described in the beginning, first third of this class. And now we're just putting them together in new and creative ways. So what's different here to the standard LSTM that we already covered last week? Well, we now have potentially multiple children inside, and we still want to compute one final vector for the parent that now describes those 3 children. And so the first thing we do is we just basically sum up the children, and we have this h tilde here. And now for our input and output gates, we just have the summed vector of all our children instead of having just the single vector from the previous time step. And one twist here is also that we actually have a different forget gate for each child. What does that buy us? Basically, the idea here is that if I, for instance, look for sentiment, and I have this movie, which was about a bunch of content words, was not good, then I really don't care about all these content words for the most part. I really care more about the sentiment words. And so the forget gates here could basically allow you to ignore certain words that don't matter as much for the thing that you want to predict. That is basically the main intuition here to walk away with. And so again, we have these h tildes. We sum up the children. We have a specific forget gate for each of the children. And then we just sum up our main memory cell here, where we multiply each of the forget gates with that child's memory cell. And then we have the same output gate and compute the final vector h. So again, here we'll have a bunch of h's coming in from the previous children now, not just a single one from the previous time step. And we again give an output h that now represents that cell. And once we have that h, we can use the same kind of softmax classifier on top of that to predict the class. So that is a lot to digest. And again, this kind of class today is more about the intuition of an exploration of what's out there. But are there any questions about these equations? All right, so this is a nice large table that will come out with this paper where we basically look at a bunch of different models, and several of these you actually now know. So here we had our deep bidirectional recurrent neural networks that we described. Here are the 3 models we covered today. One of the models we will describe after the midterm is actually a convolutional neural network. These CNNs here, these 3, except the paragraph vector, these 3 here are basically convolutional neural networks, another kind of model we'll cover in class. And then we have here our standard LSTM, a bidirectional one where we go from left to right and from right to left. We can make those deeper and combine them in bidirectional ways. And here we have our tree LSTM, the model I just described. And one interesting distinction here is that we can basically not tune the word vectors. We can just take the original glove or word to word vectors and fix them. Or we can actually allow the model and backpropagate into the word vectors. And if we do that, this model gets us the highest accuracy in terms of fine grained, so very negative, negative, neutral, positive, very positive kind of classification. All right, so that's sentiment. The last task that is actually very interesting, and I alluded to in the beginning of the class, is semantic similarity. And this is very relevant if you want to do, build a summarization system, for instance, for various other kinds of tasks. And this is really the better way to evaluate than the paraphrase classification, which is either 0 or 1. This kind of basically data set comes from a competition, actually from last year, where they collected a bunch of sentence pairs and asked multiple people to evaluate how similar these 2 sentences are on a scale from 1 to 5. And so here, let's look over these examples. A man is jumping into an empty pool versus there's no biker jumping in the air. It's basically not very related. It just gets a very low score of 1.6. But this sentence here, 2 children are lying in the snow and are making snow angels versus 2 angels are making snow on the lying children. Well, so it's not quite the same. So it's still not a super high score, but at least some kind of similar activities are happening here. And then we move on to more and more similar things. So the young boys are playing outdoors, and the man is smiling nearby, and there's no boy playing outdoors, and there's no man smiling. So these two here, you would think are describing kind of different things, but they're still quite related in several ways, in that they're the same kinds of actors are being described, same kind of activities are being described, just you have one is actually negated. And then here we have two sentences that are really very similar. A person in a black jacket is doing tricks on a motorbike, and a man in a black jacket is doing tricks on a motorbike. Very similar sentences, basically close to 5 in their relatedness score. Now, on that kind of data set, this tree LSTM actually outperforms all other models. And what you often, the way you evaluate these kinds of similarity tasks is by looking at the correlation. How well does the score that you assign to how similar these two sentences are correlate with the human judgments? And if they correlate well, then you have a high correlation. That's great. You can also look at the mean squared error between your prediction of the actual value. So you predict 4.6 or something. You can just look at the mean squared error between your number and the one from the people, the annotators that labeled that. Does that task make sense? Are there any questions about the task? So now if you wanted to build a summarization system, for instance, this would be a great model. The code's also available to start with, and actually say, all right, I have different paragraphs from different places. Now do I want to include that same sentence that I had here or not? You can basically just define a simple threshold and do this. One thing that's also interesting here is the mean vectors will also get a row of 80 versus the top model being at 86. Mean squared error is 35. So again, this is a simple baseline you should implement and look at. And then here, we can basically, and this is again something I encourage you to do, look at carefully how well does each of the different models work on different sentence lengths, for instance. So here you have this tree LSTM we just described, basically is a nice upper bound in terms of the nice high correlation. But one thing we observe is that for longer sentences, all the models are actually still doing more poorly than for shorter ones. And I encourage you all to think of those kinds of plots that would help you gain insights into when does your model work well or when it doesn't. Yeah.
When does it increase?
Why does it increase again? I think at some point there's one thing that's to be said is that the longer your words, the longer the units of text are that you care about, the less you have to understand how each of the words affect each other. That is one thing. Another one is I don't know. That is another answer. We do often observe that as you get to longer documents, let's say you have a movie review, right, and you want to classify the sentiment. Well, if the author writes more and more about it, you're just more likely to eventually get what he's trying to say. Whereas there's a lot more ambiguity in shorter phrases. So maybe that is one potential explanation. All right, so again, next week we'll just go over the materials. Do go to office hours. We decided to not publish actually the solutions online, just so we don't have as much cheating if we give the class next year. So we will hand out some solutions in paper either during the class, during the office hours. So if you want to see the solutions for the problem set, please come to office hours. And make sure you can derive these two main equations from the math. I think that will be very good for both your learning experience as well as your midterm outcomes. All right, see you next week.